Tokenization in LLMs. This is the hidden layer that shapes everything. This layer is often ignored, deeply misunderstood, quietly foundational, and critical to how LLMs actually work. Tokenization is one of the first thing an LLM does and one of the last thing people think about. It happens before embeddings, before attention, before generation, and yet it shapes everything: cost, latency, context, multilingual behavior, even prompt reliability. Today, we will build a clear mental model of tokenization without math, without jargons, and without hand waving. My name is Toni Ramchandani. I am a passionate technocrat, and today I would like to share the specific insights on tokenization that changed how build with LLM. Most people approaches language model in simple assumption that the model reads text the way human do word by word. That assumption is completely wrong. LLMs never see words, they see tokens. A token is often considered as linguistic unit, but it is not. It is statistical one. Sometimes a token corresponds to a whole word. Often it doesn't. A token can be fragmented of a word, a piece of punctuation, a number, or even a leading space. From model's point of view, all of these are just symbols in a sequence. This distinction matters more than it first appears. When you write a sentence, you perceive structure like words, grammar, meaning. Before any of that reaches to the model, your text is passed through a tokenizer, a deterministic process that converts raw text into a sequence of token IDs. That sequence, not the original text, is what the model actually operates upon. This is the first hard boundary in the system. To make this concrete, consider simple word like unbelievable. To a human reader, this word has a clear meaning, but to a tokenizer, it will or maybe split into parts like unbelievable. These fragments are not chosen arbitrarily. Each appears frequently, enough in training data to be useful on its own. By learning the patterns at this subword level, the model can handle words seen before, new terms, compounded words, names, and variation become representable by recombining familiar pieces. But wait, the model can't do the math on these ID numbers. If the ID for apple is 500 and banana is 1000, that doesn't mean banana is two apples. So these IDs are sent to an embedding layer. This is a massive lookup table that sweeps the ID for a vector, a long list of coordinates that represent the meaning of the piece of the text, often called as embeddings. It is these vectors that float up into the transformer layer. This pipeline, text to token, token to IDs, and ID to vector, is a bridge between human language and machine intelligence. Once the text is converted into vectors, it enters the transformer stack. This is where thinking happens. Layers of attention mechanism look at the relationship between tokens, understanding that bank means something different in Riverbank versus bank account. Finally, the model calculates the probability for what the next token should be. Now, why tokenization had to exist in the first place? So, this is why tokenization exists at all. Natural language is open ended. New word appears constantly. Treating every word as unique unit would cause the vocab to explode, making models inefficient, brittle, and unable to generate. Tokenization is a compromise. Break the language into reusable pieces that balance expressiveness with practicality. And how we got here. It's worth noting that we didn't start here directly. Early NLP used word level tokenization. It was simple, but if a word wasn't in the dictionary, the model crashed or printed unknown. Then came subword revolution. Around 2015, algorithms like BPE started breaking words into statistical common chunks. Today, we use byte level tokenization most of the times. This allows modern models to handle emojis, foreign scripts, and even messy code without ever seeing an unknown token. We traded human readability for universal compatibility. The consequences you experience every day. Once text being broken into tokens, every practical constraint in a language model starts to make sense. This is where tokenization stops being abstract and start becoming visible in everyday use. The first consequence is context. When a model advertises a context window, 8K token, 32K tokens, 128 tokens, it's not talking about words, it's talking about the tokens produced by a tokenizer. A paragraph that looks short to human can expand into far more tokens than expected. Formatting, punctuation, code blocks, URLs, multilingual text all increase the token count in a way that feels unintuitive if you are thinking in words. This is why prompts sometimes run out of space unexpectedly. You might have experienced while using ChatGPT. Nothing mysterious is happening. The tokenizer has simply produced more tokens than you assumed. The second consequence is cost. Most production LLMs are priced per tokens. You are billed for tokens sent in and tokens are generated out. A prompt that uses more tokens costs more and takes longer to produce and occupy more memory during inference. Two prompts that may look similar on the screen can differ significantly in cost purely because they tokenize differently. This is also why small prompt changes often sometimes affect latency. The model processes tokens sequentially. More tokens means more computation, more memory access, and more time. The third consequence is sensitivity to formatting. A space is not nothing. A new line is not free. Quotation mark, bullet points, JSON structure, indentation, these are influence how text is split into tokens. In some cases, a leading space or a line break changes token boundary entirely. This can subtly affect how the model interprets structure and emphasis, even intent. This is the reason prompt engineering is often feel inconsistent. People tweak words without realizing that they are changing the tokens in a way model actually sees it. This brings us to a critical blind spot, math. To a human, 512 and 513 are just one number apart, but to a tokenizer they might be completely unrelated symbols. 512 could be a single token, 513 might split into 5 and 13. Now this is just an example. The model doesn't see arithmetic relationship. It just sees arbitrary patterns. This is why world's smartest AI can struggle with simple fourth grade math. It's not stupid, but it's numerically blind. The fourth consequence appears most clearly in multilingual behavior. Different language tokens vary differently. Language with clear word boundaries and Latin scripts often produce fewer tokens per sentence than the language with complex scripts and with no white spaces. This means that the same idea can consume dramatically different amounts of context depending on the language used. This has real implications. Multilingual prompts may hit context limits faster. Cost may vary by language. Model performance can appear uneven, and not because the model understands one language better, but because tokenization makes one presentation more efficient than another. Finally, tokenization shapes the failure model. Truncated answers, incomplete reasoning, long context, and brittle often trace back to the token limit being silently exceeded. Most of the time, we don't see that, but that's the problem. Retrieval augmented systems can fail not because retrieval was wrong, but because retrieval content expanded into more tokens than the context window can hold. From the outside, these failures may look like model's weakness, but underneath, they are often tokenizations. Constraints revealing themselves. None of This is obvious if you think in words, but if you think in tokens, these behaviors stop being surprising. They become predictable. Tokenization doesn't just prepare text for the model, it defines the boundaries within which the model is allowed to operate. And every system built on top of LLM inherit those boundaries, whether it acknowledges them or not. Now, you might be thinking that is this a universal standard? No, not at all. By now, one thing should be clear: tokenization is not universal standard. It is design choice. Different language models use different tokenizers, built with different assumption about data, scale, and use cases. This is why some sentence can behave differently across the model even before any intelligence comes to play. At high level, all the modern tokenizers try to solve the same problem: represent open-ended human language into finite, efficient vocabulary. But they make different trade-offs in how they do it. Some tokenizers favor longer tokens, some favor smaller pieces, some include white spaces as part of token, other treat it separately. Some are optimized for English heavy text, others are built to handle many language models more uniformly. These choices are very important. A model trained on one tokenizer learns pattern in the space that tokenizer defines. It learns which token sequences are common and which one are rare and which combinations are meaningful. Change the tokenizer and you will see a completely different model operating even on the same architecture. This is why GPT, Bird, Llama can tokenize the same input differently. They were trained on different data with different objective, with different tokenization scheme. What look like a minor processing difference is actually baked into models' internal representation of the language. It also explains a common surprise: switching models without changing prompt doesn't always work. Now, thinking in tokens, once you understand tokenization, the way you interact with language models begins to change. You stop thinking in terms of how long your text looks and start thinking in terms of how it will be represented. Word become less important than structure. Formatting becomes intentional. Language choice become design decisions. This shift matters most when you move from experimentation to systems. When you design prompts, you begin to see why verbosity hurts more than it helps. Not because longer prompts are bad, but because every additional token completes for limited context. Clarity is no longer just writing skill, it's a way to preserve capacity. When you build rack systems, chunking stop being arbitrary. You stop slicing text by character count or page length and start thinking about tokens boundary. And then you realize that a chunk that looks reasonable to human may expand unpredictable once tokenized and pushing the critical information out of the context window. This perspective doesn't make models smarter, it makes your use of them more deliberate. That's where more explanation begins and many answers are found. Now, looking forward, this isn't just about text anymore. Modern multi-model models like GPT-4 or Gemini treat images and audios as token too. An image is just a sequence of patches. An audio clip is a sequence of wave. To a model, a photo of cat and a word cat are just patterns from the same massive mathematical language. Tokenization become the standard interface for all reality. So where is this heading? Believe it or not, the ultimate goal might be to get rid of tokenization entirely. Many researchers are building token free architectures, at least they are trying, models that read raw bytes just like a computer does. Now imagine a model that learns directly from the binary data, no arbitrary dictionary, no math blindness, no multilingual penalties, and we aren't there yet. But the hidden layer that shapes everything might one day disappear. So, what is the final takeaway? Language models don't work with words, they work with tokens. Once you accept that, much of the modern AI stops feeling mysterious and start feeling designed.